Hello everyone, welcome back to my tutorial. In this tutorial we are going to solve fatigue analysis using code aster. For a simple understanding, I have taken a bar of 0.1 meter length. The length is 1 meter and cross section is 0.1 and 0.1, and I am applying a load of 1000 Newton in a cyclic manner. So when time is 0, the load is 0, like that I am applying it. So I have taken a material of structural steel of Young's modulus 200 gigapascal, Poisson ratio is 0.3, yield stress is 250 megapascal and ultimate stress is 460 megapascal. As we are going to do a fatigue analysis, we have to use stress amplitude with life cycle data. So this is the data for it. For code aster, the stress amplitude has to be increasing manner, so I have arranged in that way. Here we are going to do stress life approach. So if you are doing a strain life approach, we have to use Manson-Coffin data, strain versus life data. Here we are going to do stress life approach as well as linear static analysis. This is the command for calculating the damage in code aster. From damage we have to calculate life. So this is a simple formula: damage into life is equal to 1. Code aster calculate the damage by using this command. After that we have to calculate life from the damage. Similarly, we can calculate factor of safety using ultimate stress and induced von Mises stress. Now we'll solve this problem using salome. I'm just opening salome. Yes, now it is got open. First we'll model our geometry. As you can see, to understand the fatigue analysis in code aster, I have taken a simple geometry of bar. So we can directly take a box construction. Length is 1 meter. So this both dy and dz are 0.1 and 0.1. Just apply and close. You will get this geometry. Then we'll create a groups to apply the boundary conditions. So left side we are going to fix it. I'm just naming as fix. Right side I'm going to apply a load. Now you can check it. These two groups I have created. Now we can save this file, then we'll continue it. The first case is static fatigue. I'm just saving here. Here we are going to do linear static analysis with the fatigue calculation. If you want to capture non-linear material property also, we have to do non-linear analysis, then we have to calculate fatigue data. In this case we are going to do linear static analysis. First we'll solve linear static analysis, then we'll calculate fatigue or life of the component. So it's a simple, we have created the geometry, then we'll create a mesh. For this case I'm just going to create tet mesh. .03, just say OK, apply and close. Just right click here and compute it. So this is the mesh I have created. We can check the groups also. Both the groups came here. Now we'll create a setup for linear static analysis with this kind of load factor. Now, so I'm just going to create a setup in aster study for linear static analysis with the fatigue material data. So first we'll add one by one. So I have added, first read the mesh. These are similar. Just apply and OK. Now we'll define the analysis type. This is the finite element analysis. Everywhere. This is a mechanic analysis and 3D. Just say OK. Just apply and OK. Then we have to define the material. Before defining the material, we have to give this Euler curve data, stress amplitude to life cycle data. For that, we have to create a function. Go to function, define function. This is, I'm just naming as Euler coordinate. This is, just make it sigma. Then reso name, anything we can give, we can leave this one. The very important thing is we should not go it as default. We have to give it as logarithmic curve. This one is the logarithmic curve. So we have to go use the interpolation is logarithmic interpolation, change this into logarithmic. And right side extension and left side extension, we make it linear. Or we can make it constant also. I'm just giving linear. Okay. This is very important and giving in stress amplitude life cycle data. Okay. Otherwise, default it will take linear. By using a default, it will not give the proper result. So logarithmic data has to be given. Okay. Interpolation has to be logarithmic. Now we just go to coordinate edit. Now we have to enter the stress amplitude to life cycle data. That data we have here. By entering one by one, it will take time. Here there is an option called we can directly import the data. For that we have to save it as CSV file in a comma separated file. So now I have the file. Here I have the file. I'm just opening it here. Here you can see when the stress is this much value, the life is this. Like that it is. While stress increases, the life is decreases. I just enter like that way. Because in CodeAster, the stress has to be increasing manner. If you go for ANSYS, in the reverse way it will show. Now we have to enter like this way only. Now we will save this file as a .csv file. Just go here, save as, change this into .csv, just save it here. Just save OK. Now I have saved the file. Here we'll import this data. Just go here, just open pictures, CodeAster, just open it. Now we have imported this data. Now we can plot it also. It will show error. Just leave this one. Just say OK. Just apply and OK. Now you can see. Now we have created this stress amplitude to life cycle curve. This has to be given input of material data. Then one more thing is Young's modulus and Poisson ratio. Now we'll define the material. Just go to define material. I'm just giving steel material data, linear isotropic. Now we'll check the material data here. Young's modulus is 200 gigapascal and Poisson ratio is 0.3. Now we are not focusing on nonlinear properties, so this is not required now. Now we'll enter this data here. 200 e power 9 and the Poisson ratio is 0.3. Just say OK. Just apply. Now the one more data is this stress amplitude. Euler curve has to be given as an input. For that, just type it as fatigue, FAT. the command will come here. Just edit. There are different way we can give. If it is strain life approach, if we can give Manson coffin curve. This is actually a stress life approach. For that we have to go for Euler curve. Just choose this Euler function. Okay, just save OK. Just apply, save OK. Now this is the command will read. Then now I have defined the material. Now we'll assign the material to the model. Just go here, assign a material, mesh and model, edit everywhere. This is the steel. Just save OK. Just apply and OK. Now I have material data I have defined. Now we can create the boundary condition. Before that we'll create time step functions. Then load factor function. Define a function. Now here you can see we have to apply the load in a cyclic way. So one cycle we have to apply it. So I just load multiplication coordinate. Here we have to choose time. This is we need to modify it for this. Just edit it. When time is 0, the load is also 0. When time is 1, the load is 1. When time is 0, the load is 0. When time is 3, the load is -1. When time is 4, the load is 0. Whatever the load value we are giving, then we'll multiply the data with the 1, -1 and 0. That is the way the load will get applied. So this cyclic load we are applying. Just say OK. Just apply and OK. Now load multiplication function we have created. Then we'll create a time functions. So deflist real and deflist inst. Deflist real debut start with 0 interval until 4 seconds. You have to run step. This one is we can make it 1. It will do 4 iterations. Just apply and OK. Then if it is not converging, we have to go with auto time step method. Automatically it will adjust the time step. Just say OK. Just apply and OK. Now everything I have created. Now we'll create the boundary conditions. Just go to BC. Assign a mechanical load. In left side I have to apply fixed boundary condition. So I'm just name it as BC. So enforce degree of freedom, just add it here, just edit it. So group of element, you have to choose fix, just say OK. Blockage also we can apply, or we can fix it X, Y, Z direction. I'm just fixing here, just say OK. Just apply and save OK. Now I have created the BC fixed boundary condition. Then we need to apply the load. Load 0 it's coming. I'm just leaving here. I'm just want to apply as a force. Force, there is option called force space. Just edit. Group of element, load, just say OK. X direction I have to apply the force. Actually there is no command to apply force in the code aster. We have to apply it as a pressure only. So we have to convert this force into pressure. For that, go to variable, add a variable. The force value, how much we have to apply is, so the force value is 1000 here. So 1000 divided by area we have to do. So 1000 divided by 0.1 into 0.1. Just close the data. So this much value is the pressure we have to apply, that is equal to the force. So now just say apply and close. Now just say OK. Just apply and OK. As we are applying a 1000 Newton force in this right side face, how it will apply is, it will apply as a cyclic load. When time is 0, the force 1000 Newton is 0. 0 Newton will apply. When time is 1, it will apply 1000 Newton tensile force. When time is 2, the load is 0. Then time is 3, the load will be compressive load minus 1000 Newton. Again when time is 4, the load is 0. Like that it will apply. Now I have created the groups on boundary condition. Now we'll go for analysis. This is actually a static mechanical analysis. A simple case, 4 static analysis it will do. That is a way. There is no time in this static analysis. It will do 4 static analysis. When step 1, step 2, step 3, step 4, step 5, like that it will solve. Now material, here there is a loads. There are 2 loads, edit. First one is BC, just say OK. Second one we have to choose load 0. Multiplication function, we have to choose load F. Just scroll down here, load F we have to choose, just say OK. Now time step list, we have to choose the list, this one. Then remaining thing you keep it nothing, don't change it anything, it will take default. Just apply and OK. Now what it will do, it will create the displacement as a primary variable. Now we have to check the one miss stress everything. For that just go to post processing, Paul Champ. Here there is an option called reuse the input object. Just make it tick. Here I have to check with criteria. So first one is one misses LNO, SIEQ LNO and SIEQ node. Only 2 property I want to calculate. Remaining I don't want it. For fatigue analysis we'll calculate. Just apply and OK. Now we'll save the results in MED format. So just navigate the file. This is, I'm name it as result static dot rmad, like that I'm naming it. Just edit, make mesh. Here we have to choose call champ. There is tau champ, just make it S. Just OK. MED format, just apply and OK. Now we have created the setup to do the static analysis in 4 steps. Now we'll solve this case, then we'll calculate life cycle from this static analysis result. So I'm just saving this file. Now we'll solve this case. I'm just making to 5 seconds. Run the current case, just run it. If any error comes, it will show in the message window here. Then we'll modify it. Now it started reading the command file. Now it is solved without any error. Here you can see diagnostic job is OK. Now we can check the results also. Now we just go to post paraview. Now we'll check how the load is getting applied. Then right click and open. Pictures, code aster. The file is result static.rmd. Just select and OK it. Just apply. So displacement will check. When time is 0, the displacement is 0. When time is 1, it is applying the load. When time is 2, the load is 0. So this one will read the data first. Initially the software, the paraviews, we would take sometimes to read the datas. Otherwise what we can do, there is an option called rescale the data over all time step. Just rescale it. Now see the first time step, there is no load is applying. The next steps it is applying, but we have to do with this. So here the displacement is 0. Here we are pulling positive direction. The maximum displacement is 5 into 10 power minus 7 in x direction. Then the third load, here you can see the third 0, 1, third one is 2, 2 and 2, the load is 0. Here you can see 2, the load is 0. Here you can see there is no displacement, all are 0. Now again go here, there is fourth point, it is a negative direction. Now the fourth one, here is, see, it is getting compressing. The displacement is minus 5 into 10 power minus 7. So whatever the load we are applied, it is applied correctly. From the displacement we have viewed, we can view by using wrap by vector also. Here you can give some value, just apply. Now we can animate. This is first one, second, third, compressing, 0. So like that we are applying. Now stress also we can check. This one is the von Mises stress. Now we can go for here, just apply. So it is getting a stress of, maximum stress value is when time is, now we just go to first on us. So maximum stress is 1 into 10 power 5 everywhere, because we are just applying the 1000 Newton force. So 1000 Newton by cross sectional area, we are getting a stress of 1 into e power 5. Here it is getting little more stress. Now we'll calculate life cycle, and now we'll do the fatigue using aster. Now I'm just deleting these two. Now just go to aster again. Go to aster study. Here you can see now we have done the static analysis. Now we'll calculate the fatigue data. For that, just go here, case view. Here add one more stage, that is called stage 2. Here for fatigue analysis, it is required to calculate Gaussian sigma, Elga sigma. So you just go here, there is an option called post processing, use a calc champ, go to criteria here, just add it here. We have to calculate the option called equivalent Elga. This has to be calculated from the mechastatic. These two I'm just switching on it, just apply and OK. This is we have to calculate from the previous data, so just reuse the input object, so then only it will calculate. Just apply and OK. Now the same name only it will come here. Then we'll calculate using a fatigue. Just go to option called fracture and fatigue. There is a first option called fatigue. Instead of field, what it will do, it will calculate damage only. So I'm just naming as damage. Type of calculation is cumulative damage method. Options, so Doma Elga sigma. This from the Gaussian point it will calculate the damage. And history is calc champ. And equivalent GD we have to choose von Mises signed. Just say OK. Then damage we have to choose Euler function. Material is steel only. Here the degree function we have to choose Euler curve. Just say OK. Now damage we have set up, we have created. Then finally we have to save the results in RMD format. Go to output. There is an option called set output results. Now we'll save this file. Result fatigue.rmd. For easy understanding of fatigue data, just edit mesh. Previously we have chosen result. Now this damage is nothing a field, so we have to go for field damage. Here there is an option called tau champ. Yes. Now just say OK. In format make it MED. Just apply and OK. Now we have created the stage 2. Just save this file. Now just go to history view. We'll run the case. So just go here current case. We can run both the case simultaneously by giving first case run. But what we have to do, we have already run the stage 1. So we have to reuse the previous case and solve the second stage. So I'm just want to reuse this previous case, solve the first case. If you want to skip the previous case, we can do this one, but anyway, in this case we have to take the results from the previous case. So we have to reuse it, and here we just make it run and then run it. Now see here, it is taking stress data from the previous case, previous static analysis result, and it's calculating the stage 2 and doing the fatigue analysis, and it calculates the damage. Now it see, now it is reading the command file, and it is solved without any error. Here you can see diagnosis job is okay. Now just save this file. Now we'll check the results using paraview. Just go to paraview, right click and open. In same folder, here you can see there is a file called result-fatigue.rmd. Just select this file and say OK. Here you can see the damage is calculated here. Now just apply it. Now the file is came. Here you can check there is no damage field. So how to get it is, just go to filter. There is an option called mechanics. Here just go to ELGA field to Gauss point Gaussian or to surface. So Gaussian value to surface we can go. This is I'm just naming as damage. Just apply it. So after applying, you can see the file like this. Now just go to solid color. Here you can see damage. So this is the damage value. This is actually a damage. So damage is 2.9. Almost values are equal. Damage is 2.9 e power minus 7. Now the aim is to calculate life. Now here in PPT you can see it, life is equal to 1 by damage. Simple formula we can calculate by using a calculator. Just go to filter. There is an option called data analysis. Just select this result fatigue. Just go to filter, data analysis, just go to calculator. I'm just naming this as a life. Here this is the calculator function. We can use any function to create any formulas. It's a simple function, just 1 divided by damage. So just that is a scalar data. Just click here. I'm just deleting here. Damage, go to filter. So we have to choose damage, then from that just go to data analysis and calculator. So from the damage to it has to become, now just 1 divided by scalar is damage. Choose damage, you will get damage. Result value, just rename it to life. Here also we can rename it as life. Now just apply it. Here you can see automatically damage and life is coming. We have to view the result of life. Now the life is 1 e power, 3.5 e power 6. Everywhere it's coming 3.5 e power 6, very closer value. Here 3.5 only it's showing. To view more numbers, I'm just changing here into 6.4. Just apply. You will get all the values are almost equal. So 3.47 e power 6. The life is coming 3 into 10 power 6 cycles. Now this one is the damage, and from that we have calculated the life. Now we just want to calculate factor of safety. For that we have to import these stress data. So stress data we have saved as a separate file. Just open the previous file, result.static, just say OK. Just apply. The previous life am I adding it. Now we have 1 meter stress here. From that we will calculate. First we go to filter again, data analysis, calculator. Factor of safety is nothing but sigma ultimate stress divided by induced 1 meter stress. Now this one is FOS. Same calculator. First ultimate stress. The ultimate stress of this material is 460 megapascal. That means 460 into 10 power 6 pascal. Here I am using Newton and meter units. So 460 E6 divided by, we have to choose a scalar of 1 meter stress. So this 1 meter stress we have to choose. This also I am name it at FOS. Just apply it. Here you can see it is calculate the factor of safety. The factor of safety is more than 20,000. No, it's not calculated. $460. I'm just adding 0, and this is I'm putting into bracket. Now just apply it. Now we'll do this again. 460 E6 divided by open bracket scalar Reslin 1 versus and close it. Now this data has to become correctly. So Reslin SAQ 1 versus, just apply it. Now here you can see FOS is calculated. So the factor of safety is this is the factor of safety. Here the factor of safety is 4.5 10 power 3 we are getting. So in this way we can do fatigue analysis using Codaster. So thank you for watching my videos. Please subscribe my channel for more videos. Thank you.